Good morning. My name is Neihad Al-Khalidy. I am a technical director at SLA Consulting, and SLA is a global environmental company. And my topic for today is the determination of flames plume characteristics utilizing computational fluid dynamic and experimental approaches. I will start with a very short background on the impact of plume rise on aircraft safety. Exhaust plumes that originate from power stations and flaring can cause can result in a potential hazard to aircraft operations. And high temperature or velocities may cause air disturbance and have negative impact on aircraft stability. And in extreme circumstances, it may cause airframe damage. To lower the risk of a plume rise on aircraft safety, legislations have been developed to assess the potential of a plume to affect the safety of aircraft operations. And in 2015, the US Federal Aviation Administration adopted a modeling tool called MITRE EPA as the assessment tool for assessing the impact of a plume rise on aircraft safety. And the Civil Australian Safety Aviation set up a procedure to assess new proposals that cause a plume rise. It's basically the procedure starts with a screening method just to measure the velocity at the exit of the stack and then implement EPA model if necessary to determine the probability of an aircraft experiencing turbulence near the plume rise. And if you want to use the EPA, the MITRE EPA model, then you need key input parameters, including effective height of the plume at the equivalent exhaust emission point, effective diameter of the plume, velocity of the plume, and temperature of the plume. For many scenarios, like we don't have measurement for the key input parameters, and assumptions are made to approximate these parameters using conservative model, such as Ohio model. These assumptions lead to inaccurate results of simulations, and the current study provides or presents CFD as a tool to provide a more reliable key input parameter to EPA models. And the main objective of the study are to assess the fuel combustion, model the combustion process to estimate the chemical reacting species and associated energy due to chemical reaction, predict the speed in the three directions, pressure profile, temperature, and turbulence parameters, and then predict the participating radiation during the combustion process and predict the impact of various atmospheric wind conditions on the flume characteristic. For example, looking at a breeze or a near calm wind condition or a windy condition. I have also assessed the impact of air to fuel ratio, the impact of it on the flame plume, because for many scenarios, we don't have enough info on the air to fuel ratio. And finally, determine the flame plume characteristics like effective height, diameter, temperature, and velocity. A mobile purge burner trailer is used to burn off residential gas near Sydney Airport. And this was like as part of the realignment of gas pipelines due to a new infrastructure project. And this process is important to avoid release of natural gas to atmosphere. It's like an environmental regulation and prevent a natural gas plume gathering in airspace. And the system consists of a twin stacks and the compositions of the fuel is like 88.8% methane, 7.8% ethane, and 1.9% CO2, and some small percentage of N2 and propane. And it is conservatively assumed that the fuel consists of 100% methane. It's a conservative assumption because methane is more flammable than ethane. And I have also used like a generalized eddy dissipation model to analyze the combustion system. This model is very good when the fuel is burning quickly and the overall chemical reaction is dictated by turbulent mixing. Uh, and it is implemented in many commercial software like ANSYS Fluent, the one I use for this study. And most importantly, this one is validated against measurement data as well. So just showing an image from the CFD model is very accurate when you compare it to the actual system. And you could see here also like air is introduced through an annular inlet. Then there is a disk intake where the air is entered into the system, and this has been included in the CFD model. And as previously mentioned, this model accounts for the impact of the approaching winds on the flare characteristic. We are just showing the trailer inside the computational domain. And I have also provided some information about the discretizations, just to make sure we got an accurate numerical solution. And for the current analysis, I have used the polyhedral elements with a total of 11 million nodes to cover the computational domain. And I got a Y plus in the computational domain in the order of 54. It's basically I got fine elements almost in the entire domain. And I have used the realizable K epsilon turbulence model as well. And this is a more accurate than the standard K epsilon. And it is used for many industrial problems. And then it's got a better equations for the turbulence viscosity. And also the dissipation is being derived based on some analytical solution. But obviously you could use even a more advanced model if necessary. And furthermore, like I have used a advanced like radiation model just to predict the participating radiations during the combustion process. An iterative procedure was used to estimate the chemical reacting species and associated energy due to the chemical reaction, and then all other variables as well as being solved iteratively in the computational domain. And this image to the right, just showing the example of the final mesh in the domain. You could see here, it's very fine mesh in the combustion chamber, like it was almost in the order of a couple of millimeters at some locations where we got a nozzle. And here, this image to the left showing the scaled residual history. And this is all the variables you see being reduced by at least 10 to minus 4 to 10 to minus 7, demonstrating a valid numerical solution. This part of the results shown in this slide. Figure A showing the mass fraction of methane. You could see pre-combustions, we got 100% of methane, and then start to mix with the air, and then the mass fraction of methane starts just to reduce gradually once the chemical reaction starts. And the figure B showing the mass fraction of O2, it is in the air is 23% as per the given boundary condition, but where the reaction is occurred, you can see the oxygen is reduced and in the combustion chamber and above the flare tip as well. Figure C showing the mass fraction of CO2, it continues to rise, in fact, because due to the increase in the methane consumption. And figure D showing the mass fraction of H2O, and I have predicted like almost 13% of water due to the chemical reaction. And this is in a very good agreement with the data in the open literature. This figure showing the mean flow velocity at a 2D section through the system. And I have presented the results on a color-coded contours between 0 and 28 meter per second. The dark blue representing the near calm wind condition, and then 26 is the strongest speed in the domain, and you see there is a nozzle at the base of the combustion chamber where, due to the nozzle, the velocity of methane is increased to 25 meter per second, and then reduced again at the tip of the flare due to the diffuser arrangement of the venturi. Uh, this figure showing the static temperature and mean velocity results during near calm wind condition. And this is ISO surface. It's basically a 3D presentation of the plume. And the top figure showing the temperature, you see the red inside has got 1,000 degree, and then the green is 480 degree. And then the same here for the velocity. I have introduced another function at the tip of the flare just to calculate the area weighted average of temperature. Rather than, in this case, I could include all the cells into account rather than just relying on the maximum and the minimum temperature. When you do various scenarios, then you could, based on this parameter, just to see the impact of each scenario on the submission. Here, just showing the results for the near calm wind condition again. I looked at the impact of the ambient temperature. When the ambient temperature was reduced to 5 degree with no change to all other boundary conditions, like I found the temperature at the area of interest, in this case is 7.1 meter above ground. This is required for the EPA model. Uh, Slightly increased to 481. Previously, we got 480, and vice versa. When the ambient temperature was increased to 35 degree, the temperature at the area of interest is reduced to 470 degree. There is some impact, but it is not a major impact on the results of simulation. Here, just showing previously, I looked at the poor combustion scenarios. In this slide, I just assessed the impact of higher air-to-fuel ratio. And basically, the combustion is more efficient. And to the left, you could see the results for the near calm wind condition, and ambient temperature is 15 degree, and wind speed is 0.1 meter per second. You see the temperature is significantly increased compared to the previous scenario due to the improved combustion efficiency. And the figure to the right is showing the impact of the wind speed. The wind speed is increased slightly from 0.1 meter per second to 0.28 meter per second. You could see the temperature is reduced at area of interest, at the same time the velocity as well. Therefore, it is a very good thing when the ambient wind speed is increased, then we have more mixing. Here, just more output from the CFD results. This is just showing the equivalent diameter of high temperature. And you see with the CFD, once you got a valid numerical result, it's very easy to post the process and present the results the way you want. You could look at any 2D sections, and then you could easily look at the equivalent diameter of the plume, equivalent speed of the plume, and equivalent temperature of the plume. And you could then use this for the EPA model. And the worst case plume results are obtained when near calm wind conditions coincide with low ambient air temperature and the natural gas is combusted at a high efficiency. I got a temperature of 620 degree and equivalent plume diameter of 1 meter. And then when you compare this to the conservative or higher model, it's significantly lower. Then it was, you could get like 1,000 degree, and therefore it will not give you the right or correct results of simulation. That's why the tool is important to use and provide an improved set of input to the EPA models. And Subsequently, a test was carried out for a similar mobile trailer system. It was, in fact, one little difference here. The distance between the center lines of the stocks was like a 700 mil higher than that in the CFD model. And this is uncontrolled test condition. Like we got a ambient temperature of 21.6 degree and ambient mean wind velocity of 4 kilometer per hour, and lower wind speed are anticipated at the test locations due to the shielding from suburban buildings. And it was no rain during the test condition as well. And infra video camera was used to measure plume details, and the video was placed at a distance of 50 meters from the system, and spot readings were taken at a number of locations. And here, for example, SP1 and SP2 is 5 meters above ground, and SP9 and SP10 22 meters above ground. And you could see the temperature, the mean temperatures ranging between 440 and 500 degree, and then the extreme range from below image is up to just below 600 degree. Therefore, the results is very, very good agreement with the CFD results. And also you could see like the plume temperature above the system drop very quickly. And this is again in line with the CFD results. Could see just in a few meters reduced from a 500 to ambient temperature. Just I will end the presentations with a couple of major conclusions. Like the current study provides a novel approach to use a combination of computational fluid dynamic tool and EPA models to reliably predict the risk of turbulence and upset being encountered by a range of aircraft types that operate through a rising plume. And a CFD model has been developed to determine flame plume characteristic like effective height, effective diameter, temperature, and velocity from two flare stacks, which are part of a trailer-mounted mobile purge burner system. In fact, this could be used for any other system. This was only an example. Any other combustion chamber could be modeled using this methodology. And a subsequent experimental test of a similar trailer-mounted system has validated the CFD results. And the CFD simulations, the current study accounted for the turbulent flow with chemical reaction mixing and reaction, utilized an advanced radiation model to solve participating radiations in the combustion zone. And I think just the last image, there are a few more real life problems where we use computational fluid dynamic to solve industrial problems. Thank you very much for listening, and I'm ready for your questions.